welcome to our fourth learning workshop, uh, balancing chemical equations and predicting products. So some of the stuff may seem a little bit more rudimentary, but we're going to get into stuff that's going to be much harder very quickly. Um, and this a lot of this stuff really is foundational. Unfortunately, I do see a lot of cases where students go on to Gen Chem 2 and even organic chemistry, and they don't remember how to do some of this foundational stuff like write a balanced chemical equation and like that. So um, first things first, have you covered this in class yet? Is this something that has shown up in your classes? The balancing
I've seen
equations
a
and predicting.
pretty fair amount of this. It just seems integrated into what we're learning. It's not been like a
Sure.
separate topic.
Okay. Are you already in stoichiometry then?
I just got into stoichiometry.
Okay. Stoichiometry is going to be our next session next week. Um, and please let me know if I am starting to fall behind where the professor is. I can always jump an extra session, like do an extra session in a particular week so that we can get caught up. But I don't want to leave you hanging. But next week is going to be a good session. It's going to be stoichiometry and limiting reagents. Um, but let's go ahead and jump into this. So basically, for chemical equations, and like I said, this is going to be maybe a little bit obvious for you, but um, we write chemical reactions or we express chemical reactions using chemical equations. And the chemical equations indicate reactants on the left side and products on the right side, which is going to seem pretty normal if you're, your standard English / European, um, language speaker. For if you're from a culture where you actually do not read right to left, but you actually might read left to left to right, you actually might read right to left. This might seem a little bit weird, but this is going to be reactants going to form products. So sometimes what'll happen is you'll be given a question where it'll describe a chemical reaction to you, and you're going to have to write a chemical equation from that description. And so what we did, I think maybe last week with the week before with writing chemical formulas for ionic and covalent compounds is going to be very important here. We're going to actually follow up with that. So also, one of the most challenging things for students sometimes is balancing chemical equations because they're like, okay, well, I know how to balance, I know how to do algebra, but when you start throwing in letters and numbers, things start to get a little bit confusing. Okay, so let's go ahead and jump right into this. Our question number 1 says, aluminum and oxygen make aluminum oxide. So aluminum, of course, is just going to be Al, right? And it says and, which means that this is a separate substance and oxygen. So what's oxygen? What will I write for oxygen? O2, very good. Yeah, because sometimes people might assume that this is going to be just an O, but there's actually a list of 7 elements. I'm actually going to go ahead and list them out right here. 7 elements where you have to actually take into account the fact that when they're by themselves, they are diatomic. They don't exist as separate elements. So there's 2 little acronyms we like to use. B. Brinkelhoff, Br, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So when they're by themselves, so it does not count when they're part of a compound. It does not count when they're an ion, but when they're by themselves in their elemental form, they're going to exist as diatomic molecules. They're not stable otherwise. So yes, this is O2 then. And I think, somebody said something. Oh yeah, there you go. I bring clay for our new house. That works too. That works too. I like that. That's much easier than hamsters never invite our class for brunch. Good call. All right. So Now we have to figure out what the product is. Now when we're in this case, the product is given as aluminum oxide. So is this an ionic compound or covalent compound? Ooh, it's not covalent. You can tell because anytime remember, covalent compounds are when you have just only non-metals. But when you have metals and non-metals, then, yeah, when you have metals and non-metals, you get uh, an ionic compound. So this is an ionic compound, which means we're going to have ions, and it means you have to uh, find the charge, right? So what's the charge of aluminum? In an ionic compound, what's the charge of aluminum? Yep, 3 plus. And what's the charge of oxygen? Yep, so that's 2 minus. So if that's the case, I want to put this together as a compound. I have to make sure the total positive has to be equal to the total negative. So what's the formula that's going to work for this one? Al2O3. Because the lowest common multiple of 3 and 2 is 6. I need 2 aluminums to get me a total charge of 6. And I need 3 oxygens to give me a total negative charge of 6. So now I can balance this. And I'm going to balance it. I usually like to list out my elements. So I'm going to list out aluminum and oxygen. There's only 2 elements in this case, so this is pretty easy. And now normally when you're balancing these equations, you want to balance whatever is easiest to balance first. The element that is easiest to balance first. Now the easiest one to balance is going to be the one that appears in the fewest places. So each different substance, each different separate element, if it's an element in its elemental state, or a compound if the elements are chemically bonded, each substance, I want to balance the element that is present in the fewest substances because that's going to be the easiest one for me to balance. In this case, both of these, aluminum appears in 2 substances. It appears in aluminum and aluminum oxide. And oxygen appears in 2 substances. So it doesn't matter which one I balance, it's going to be equally easy either way. So if I ask, how many aluminums are on the left side, or I'm going to start with 1. How many oxygens? It's 2. On the product side, how many aluminums? 2. And how many oxygens? 3. So, like I said, it doesn't matter which one I balance. So which one do you guys want to balance first? And what do you do? Which one should I balance first, aluminum or oxygen?
Oh, I think you're supposed to technically do aluminum first, right?
Actually, it doesn't matter. They're both equally easy to balance.
I thought you're
But yeah,
supposed to do metals and then hydrogen and then oxygen, or something like that.
not necessarily. So yes, you're not wrong that usually works to do metals first, then metals first, then non-metals other than hydrogen and oxygen, then hydrogen and then oxygen.
Right.
But that is not actually that's not actually foolproof. There's actually cases in which that's the wrong thing to do.
Really? Shoot. Okay.
Yeah.
That explains
So,
a lot.
and I can give you some cases in which that would be the case. But usually you want to balance whatever's easiest to balance, and that is whatever appears in the fewest places.
Right.
And logically that makes sense. Because if something only appears in 2 places, once on the reactant side and once on the product side, I know that to balance it, I only have to change one thing on the product side to make it the same as on the reactant side.
Right.
However, if it's in 2 or 3 or 4 places, I have no idea which one I need to fix.
Exactly. That's pretty cool. I like it.
Okay, so cool. So Cody's saying aluminum. Let's go ahead and balance aluminum first. Sure. Why the heck not? And what would I do to balance aluminum? Yeah, put a 2 in front of what? Yeah, right? And you can feel free to talk. I like it when you guys talk. It's kind of fun. So this is going to be a 2 in front of aluminum. Now, the thing to keep in mind here is that these coefficients are multipliers. They multiply what's in front of them. Of course, obviously, a positive charge is going to block it from multiplying anything beyond that. For for example, like if I have 2x plus 3y, I don't say, oh, well, that's 6y. Because while it's true that the 2 multiplies times the x, it does not multiply times the 3, right? That does not happen. So same thing is true with these chemical equations. So 2Al plus oxygen. Now I have 2 aluminums here. Now I have to balance my oxygens. Whenever, this is a little tricky because whenever you have an odd number that you're trying to balance with an even number, there's no way to do that unless you use a fraction, but you can't use fractions. You can't use fractions in balancing equations, so what do? Well, whenever you're balancing an odd with an even, double the odd to make it even. Double the odd to make it even and then rebalance. So in this case, I'll put a 2 in front of the aluminum oxide, and that's going to multiply times the aluminum, and it's going to multiply times the oxygen. So how many aluminums do I have on the product side now?
4.
4. Very good. And how many oxygens do I have on the product side?
6.
6. Excellent. So 4 aluminums and 6 oxygens. Well, now I'm unbalanced again on both fronts. So I'm going to have to rebalance the aluminum. So what do I do to rebalance the aluminum?
You put a 4 in front of that, and then you put a 3 in front of the other oxygen?
Exactly. I put a 4 in front of the aluminum. That'll change this to 4. And then I put a 3 in front of the oxygen. That'll change it to 6. Cool. So now I'll go ahead and proceed to do the next one. It says sodium hydroxide and hydrogen sulfate produce sodium sulfate and hydrogen hydroxide. Now, in truth, some of these names are not, they're not actually the names of elements properly or the compounds properly speaking. We would never call hydrogen hydroxide hydrogen hydroxide, because hydrogen hydroxide is HOH, or in other words, water, H2O. Although it was kind of funny, there was actually a, and we can't remember if it was led by a student or a chemistry professor who came along later, but the student decided to play a prank on the college campus and led this campaign saying that, basically saying the school needs to stop poisoning your students, ban dihydrogen monoxide. Of course, you know what dihydrogen monoxide is, H2O. And like there's they pulled out like all these stats or whatever, like this many people die of dihydrogen monoxide every year, et cetera, et cetera. Dihydrogen monoxide causes such and such problems. Well, of course, if you drown, yeah, you die of dihydrogen monoxide. So they had this ridiculous campaign, and most of the students who weren't like chemistry majors were like all fired up. It was like, yeah, stop the poisoning, stop. They're trying to ban water on campus. It's pretty great. Shame on me. So yes, hydrogen hydroxide is water. Yeah, I think it might have gotten around on the news. It was pretty funny though. So yeah, sodium hydroxide is that ionic or covalent? What is sodium hydroxide? It's ionic, very good. And what, yep, it's NaOH. Yeah, because sodium has a +1 charge, and hydroxide is OH with a -1 charge. So since sodium's an Na+1, and this is an OH -1, they're balanced. You only need one of each, and the formula is going to be is just going to be NaOH. So I'll go ahead and erase that. There we go. NaOH. Now you might already be familiar with how to name acids at this point. That's its and, so separate substance. Hydrogen sulfate. Now, here's an interesting thing about hydrogen. Hydrogen is actually often, it acts like a metal in a lot of cases in terms of the fact that it forms a positive ion. And actually at low temperatures, it acts like a metal in other ways too, at really low temperatures. It's kind of a quirky element. So hydrogen sulfate, H2SO4, and notice that even though it's all nonmetals, and it's a covalent compound, strictly speaking, it actually is named almost like as if it was an ionic compound. So if you were naming hydrogen sulfate not as an acid, H2SO4 not as an acid, you call it hydrogen sulfate. If you're naming it as an acid, it would be more appropriate to refer to it as sulfuric acid. Because when hydrogen is bonded to nonmetal ions or polyatomic ions, it's typically always acidic. I mean, it's an acid when it's dissolved in water. If it's not dissolved in water, like HCl gas, you would call that hydrogen chloride gas. So once again, it acts kind of like a nonmetal. Hydrogen chloride, or I mean, it acts kind of like a metal, hydrogen does. And that I don't say monohydrogen or hydrogen monochloride. I don't use the prefixes. With hydrogen, I treat it as if it was a metal when I name it not as an acid. But yeah, this is sulfuric acid. So H2SO4 and NaOH go to form, they produce sodium sulfate. And of course, sodium is a +1, as you know. And sulfate is SO4 2-. So what's the formula for this? What's the formula for sodium sulfate?
Is it NaSO4?
Yep. Well, not quite. You have to make sure the charge is balanced. There have to be an equal number of positives and an equal number of negatives.
So Na positive 2, SO4 2 negative?
Yeah.
Okay.
So, well, not Na positive 2, but rather I need 2 sodium, so the Na subscript 2.
Okay, 2.
SO4.
Okay. Because of the two negative.
Yeah, well, it's actually because I need the charges to be balanced.
Mm-hmm.
So I need 2 sodium plus, I need 2 positive charges, so 2 sodium ions to balance with every 1 sulfate ion.
Okay.
And then, of course, with water, plus water. There we go. So now all I have to do is balance this. And so when I'm balancing, I'm going to actually go ahead and list my elements once again. And I encourage you to list them, at least at first, until you get more comfortable with balancing it in your head. At a certain point, you'll be able to just be like, okay, yeah, I can do this without listing the elements. But especially with more difficult equations, it's always a good idea to balance or to list out your elements. And I would always list them out in the same order so you don't get confused. So it's NaOHS on the left side. I'm going to do NaOHS on the right side as well. Okay. All right, so here's the deal. How many sodiums are on the left side?
Just one.
Just one. How many oxygens are on the left side?
5. Right?
5. You have to keep track of the fact that the oxygens are in both compounds, so that is 5. How many hydrogens are on the left side?
3.
3. And how many sulfurs?
Just 1.
1. And actually, this brings up a really good point. Well, actually, let's go ahead and list our elements on the number of elements on the product side. So how many sodiums on the product side?
2. 2.
2. And how many oxygens?
5 again.
5. And how many hydrogens?
Just 2.
And then how many sulfurs?
1 sulfur.
1 sulfur. So before I actually go ahead and just jump into balancing this, I want to actually figure out which is going to be the easiest one to balance, and I can do so by looking at the looking at the substances. So sodium actually appears in how many different compounds in this equation?
Well, are you asking how many times sodium appears in this equation? Is that what you?
Yeah.
Three
How many
times?
different substances?
Oh, sorry.
Yeah, no, Cody got it. Yeah, it's 2. It only appears in 2 places, 2 substances. How many substances does oxygen appear in? Yeah, every single one, all 4. How many times does how many places, how many substances does hydrogen appear in? 3, very good. And then sulfur? 2. So it looks like sodium and sulfur are going to be the easiest ones to balance. And then from there, I would balance hydrogen, and then lastly, oxygen. So let's go ahead and balance this. So I'll balance sodium. Well, sulfur is already balanced, so I'll go ahead and balance sodium. There's 2 on the right-hand side, 1 on the left-hand side. What do I do?
Put a 2 in front of your reactant.
Absolutely. I put a 2 in front of my reactant, put a 2 in front of NaOH. Now this is going to multiply everything, so how many sodiums do I have now? 2. And how many oxygens?
10.
Not 10.
Okay, so you don't multiply it by the 5?
No,
Oh, I see, because that's
I
your
have to,
total. You just multiply it by that 1. Okay.
exactly.
Okay.
So how many do I have then?
In that
6.
1, yeah, sorry, go ahead.
Yeah, 6. Yeah, very good. Okay. So, and then how many hydrogens after I put that 2 there? Yep, and that's going to be 4. Very good. 4 hydrogens, 2 from one compound, 2 from the other. And how many sulfurs? 1. Very good. Yeah, so that hasn't changed because there's no sulfur in that compound. So hear a little background noise. It's my precious little boy. He is nonverbal and autistic, and he makes very cute sounds. He has wandered into my room. So just so you know. And let's see. So now, after we balance the sodiums, now we can balance the hydrogens because sodium and sulfur are both already balanced. So what do I do to balance the hydrogens now?
Multiply the second, the water on the product side by 2.
Very good. And I like how you described it, multiply, because that's what these coefficients are. The coefficients are multipliers. They multiply everything in the compound. So the 2 will multiply the hydrogens and the oxygens in water. And so I'm going to have how many hydrogens now on the
4.
product side? 4. And how many oxygens on the product side?
5.
Not 5.
Oh wait, wait. Sorry, 6.
6. No worries, Elaine. I'm so sorry about that. If there's anything we can do to help, just let us know. So now you'll notice that by balancing the easiest elements first, the hard elements balance themselves.
So that
Pretty
went
cool.
incredibly smoothly. Like the way
It
I,
did.
I have a bad habit of taking like polyatomic ions and just leaving them together and just calling it OH, and
Yeah.
that kind of bites me in the butt sometimes. Makes it really
Yeah.
complicated.
It's actually it's a very interesting. Yeah, it's a very interesting question. There are a lot of professors that promote the idea of separating or keeping polyatomic ions together. I don't, and I'll tell you why. Um, One, even if it, in cases where it does work, it doesn't really make it any easier. It doesn't make it that much easier. It's pretty much about the same. And unfortunately, there's also cases where it doesn't work because you have situations where the um, you have situations where the polyatomic ion does not actually stay together. It actually breaks apart.
Oh, right.
Um,
Kind of like acids, right? Like the
exactly,
right.
exactly.
Okay, that
And
makes
in
sense.
fact, to that point, I'm actually going to go ahead and toss up an extra balancing question for you because I think it'll be helpful. Um, so let's go ahead and toss this out there because this is actually a really good practice question for you to kind of take a look at. So this is the reaction between copper and nitric acid. It's a really interesting reaction. So copper and nitric acid will react, and it will form CuNO3 2 plus NO2 plus water. So looking at this particular problem, um, I'll list out my elements: copper, hydrogen, nitrogen, and oxygen. Cu, hydrogen, nitrogen, and oxygen. Okay. Oh yeah, no problem. No problem, Wayne. Sorry. Yes, I got your message. Um. All right. So here is here's what we're gonna do. We're gonna list out our elements here, and copper. There's one over here, and there's one over here. To start, hydrogen is one here, nitrogen one, oxygen three. How many hydrogens are on the product side?
Uh, 2,
hmm How many nitrogens?
3,
hmm How many oxygens?
9.
Yeah, nine. In this case, there's three places with oxygen on the product side. 2 times 3 is 4, plus 2 is, or 2 times 3 is 6, sorry. Plus 2 is 8, plus 1. I need to go back to elementary school. Um, 2 times 3 is 4. No, anyway. So now I want to actually take a moment to look and see which of these appears in the fewest places, okay? So copper appears in how many different substances?
Just 2.
Just two. What about hydrogen?
2,
Two. What about nitrogen?
3.
Three. And what about oxygen?
4.
So I've actually listed these in the order I want to balance them. And it just happened to be that way, just accidentally. But copper and hydrogen are going to be first. It's interesting because normally you don't balance hydrogen before you would balance nitrogen. Normally you'd expect to balance nitrogen first. But that's not what you should do in this case. Um, Especially if you went by that rule that you were talking about before, metals, then nonmetals, then hydrogen, then oxygen. That doesn't always work. This is a case where it doesn't. Okay, so let's balance hydrogen. What am I going to do first to try to balance this?
Multiply nitric acid by 2.
Yep, that's nitric acid. I'll go ahead and multiply that by 2. That's going to multiply each one of these. It's going to give me 2 hydrogens, 2 nitrogens, and 6 oxygens. Now I can balance nitrogen, but I run into this situation where I have an odd number of nitrogens on the product side and an even number on the reactant side. So what do I have to do?
Have to make the odd number even.
Uh-huh.
Right. So
And
I
so I
think.
have to double the coefficient of the compound, causing this nitrogen to be odd.
Right.
So
So
which of these products should I double?
typically, when I find myself in a situation where I've got an element in multiple compounds, typically I find one that's just one. For example, the NO2.
Hmm.
So I multiply NO2 by 2, and
That's
then
exactly what you should do.
yeah.
There's a typical mistake that a lot of students tend to make is that they will actually put a 2 in front of everything that has a nitrogen in it. They'll want to put a 2 in front of here. That'll actually get you in more trouble in the long run because sometimes you only want to double what you need to, not necessarily what you don't. So double the coefficient of whatever is making it odd, and the one that's making it odd is the NO2. So if you need to double the other one, that'll show up later, but don't worry about it right away. And so the nitrogen here is now going to be 4. And what else changes by putting that 2 in front of the NO2?
It changes your oxygen count to 11.
Yep. I have 6 oxygens here, and 2 times 2 is 4, plus I have 1 from here. That gives me a total of 11 oxygens. So now I can go ahead and balance the nitrogen. So what do I do to balance the nitrogen?
You need to change the coefficient of 2 on the products on a reactant side to 4.
Yep, exactly. So I'm going to go ahead and change. I'm going to get rid of this 2 here, and I'm going to multiply this by 4 instead. And that's going to give me 4 hydrogens, 4 nitrogens, and how many oxygens?
I got 12.
Yep. So now I have balanced my nitrogen and I balanced my nitrogen and my copper. But since I've unbalanced my hydrogen, I have to rebalance that. So what do I do?
I went to water and I multiplied by 2.
Exactly. That'll give you 4 hydrogens. And it also gives you a 2 times, so this is going to be, I had 6 oxygens in the first one, 4 here. So 2 times 1, I now have 2 oxygens from the water. That gives me a total of 12. And now you see that the hardest one, oxygen, balanced itself. This particular equation I've seen students go back and forth on. It looks pretty easy when you balance it in the right order, but I've seen students go back and forth on this particular problem for literally like a half an hour or longer and not be able to balance it. If you end up trying to do it in the wrong order, or if you kind of fail to take those steps to make it easier on you, yeah, uh, it can be a problem. Hey, Cody. Yeah, no problem. And I will post this online. We'll post the video online so you can watch it. Definitely. And so you can catch the rest of it if you want. Thank you for coming. Uh, so the reactions what are the reactions called whenever acids separate? So are you talking about like the acid-base reactions or neutralization reactions?
No, you know how nitric acid just kind of fell apart
Yeah,
into,
it did.
or like in, I think like sulfuric acid. Oh, that's not right.
Well, I mean, admittedly, you can have a situation, especially like with regards to sulfuric acid, um, fuming sulfuric acid, shall we say, can break apart into water. and sulfur trioxide.
Yes. Yeah, that's what I
That's
was
just
looking for.
that's just a
Is there a
decomposition
term for
reaction.
that? Decomposition. Okay. Neat.
Yeah,
Thank you.
and you don't usually get those too often. You don't usually get those too often. Well, in terms of like the acid breakdown, but we actually are going to cover different types of reactions, which include decomposition. And decomposition reactions are not always, but they can be redox reactions, oxidation reduction reactions, and we'll go over that as well. Because redox, that's an important point. That's an important concept you need to be aware of as well. Okay, so there's one other type of reaction that I want to go through with you. Um, now let's just go through it here, and that is balancing a combustion reaction, because these are reactions that really mess students up sometimes. So let's go ahead and take a look at a standard combustion reaction, and you can uh, absolutely be certain that your professor is going to expect you to balance one of these at some point. But let's say you have something like this, C4H10, okay? C4H10 plus oxygen. And a combustion reaction always has the same products, carbon dioxide and water. Oh, combustion reaction? Yeah, well, actually, it's not simply that it's water and carbon dioxide. It's that you have a hydrocarbon burning in oxygen. All right, it's hydrogen and yeah. So because what's interesting is that, like, for example, the cellular respiration reaction that occurs inside the human body, actually you get a similar type of. It actually looks like a combustion reaction. Like if you look at the glucose C6H12O6, it actually is in some ways kind of a combustion reaction. It is exothermic, but it's a controlled combustion reaction. I guess it wouldn't be. It doesn't actually form fire in your body, obviously, but uh, it might not be. It's probably not appropriate to call it a combustion reaction, but it's the same type of thing. It's just broken down into many different steps, catalyzed by all sorts of different various enzymes and cofactors. Um, but it looks like a combustion reaction. And interestingly enough, this same reaction would be potentially possible if you simply burned sugar and you could get carbon dioxide and water. But basically, combustion reaction you can usually identify because it's some sort of hydrocarbon and oxygen, and the products are always carbon dioxide and water. Occasionally, you'll have an oxygen also in this compound, the C4H10, along with an oxygen there, or even an OH. But yeah, generally speaking, it's some sort of hydrocarbon with oxygen goes to form carbon dioxide and water. So the tricky thing about this, when you're balancing this, is that, I mean, sometimes these can be fairly easy, but sometimes it requires you to go back and forth a few times, and this is actually one where you have to go back and forth a few times, and I want you to be prepared for something like this. So, um, first things first, we identify how much of each we have on each side, how many carbons are on the left side, how many carbons on the reactant side do we have? 4.
4.
How many hydrogens?
10.
Yep. Oh, no, hydrogens 10 or 10, right?
Yes.
Yep. And then how many oxygens? Yeah, 2. And then how many on the product side? How many carbons? 1. And how many hydrogens? 2. And then how many oxygens? Yep, 3. It's interesting you said 2 or 4. What made you think it might be 4? Just out of curiosity. If you don't mind my asking.
Hi.
Yeah, why did you think the hydrogens might be 4?
I think because it's multiplied by 2 is the nearest the H2. H2O
Well,
is make
yeah.
the multiply by 2, 1 times 2.
Oh, well, I mean, so the subscript always, so that's a good point. So the subscript always refers to the element before it. So this subscript
Oh,
only refers to hydrogen. If, however, you had something like this, let's say, for example, I had PB, if for example, I had PbNO3 4, okay, this, that 4 would actually multiply what's inside the parentheses. It would multiply the 3 oxygens, so that would give you a total of 12, and it would multiply the 1 nitrogen, so it would give you a total of 4 nitrogens. So that is important to note. Anything outside of a parentheses will multiply what's inside the parentheses. But for this case with the hydrogen, no, that 2 just refers to the fact that there's 2 hydrogens, but there's no further multiplication or anything that
okay.
happens, at least not until we go ahead and put some coefficients on it. Okay,
Thank you.
yeah, no problem. So what is the first step to balancing this? What do I want to do?
Uh, balance either, or you can balance either of them, I guess. Either carbon or hydrogen, I think.
Carbon or hydrogen? How did you know that those would be the ones you'd balance first?
Just the amount of times it appears in different compounds.
Exactly. So there are 4 different substances here. Carbon appears in 2 places, hydrogen appears in 2 places, and oxygen appears in 3 places. So carbon and hydrogen are going to be balanced first. So if I balance carbon, what am I going to have to do?
Multiply by 4 on the first reactant.
Uh-huh. Multiply it by 4. So the CO2 is actually, well, not the reactant, you mean
Oh,
product,
I'm
right?
sorry, product. Yes, sir.
Yep.
My bad.
Yeah, no problem. All right, so the 4 gets multiplied by CO2. That multiplies both the carbon and the oxygen. How many carbons do I have now?
4.
And how many oxygens do I have now on the product side?
9.
9. 4 times 2 plus the 1 from the water. Okay, so now I can balance my hydrogen. So how do I balance my hydrogen? What am I going to do there? 10 on the left, 2 on the right.
Well, you might put a 5 in front of water.
Yep, exactly, because these are coefficients are multipliers. If I want to get this up, this is the only place where I have hydrogen on the product side. So I have to multiply that 2 by 5 to get it to be 10. So 5 times 2 is 10. I now have 10 hydrogens, and I have how many total oxygens?
13.
13. So now it's a little bit awkward because I have an odd number, 13, that I'm trying to balance with an even number, 2. Carbon and hydrogen are already balanced. So what do I have to do to balance the oxygen at this point?
I think the first thing I would do is bump up the 5 to a 6.
Okay, problem with that is that will disrupt any balance that you have
With
with
hydrogen.
the hydrogen on the other side. Because there's no way, if I turn that 5 to a 6, that would be 12 hydrogens, right?
Yeah.
But there's no way to make 12 hydrogens with C4H10, right?
Right.
So,
Such a weird
so whenever you
situation.
have it, yeah, whenever it is. Whenever you have an odd with an even, what do? Think
Lowest
Vegas.
common factor.
Or not even that. Think Vegas. Double the odds, right?
Okay.
Double the odds. Yeah, double the odds to
I've
make
never
it
been to
even.
Vegas, so sorry.
Well, neither have I actually. So I speak I speak not from experience. Although I, interestingly enough, had an uncle who was taken out by the mob for winning too often in Vegas. But a great uncle, he was
How
not
interesting.
yeah, like so my dad's uncle just came home one too many times with a big payday, and they didn't like that. Um, yeah, this is back when things were a little bit more shady. Not that they're not shady today, actually. Anyway, sorry. Oh yeah, so I'm going to double the odds to make it even. And the reason that I double it is because I want to make sure that I keep it in balance with the other stuff. So, for example, if I double the amount of hydrogens, it's very easy to fix that on the other side. So if I double the odd to make it even, I change this 5 to a 10, I now have 20 hydrogens, right? And how many oxygens do I have?
18.
18. Yep. So I have 18 oxygens. Now you might want to go ahead and jump in and try and balance oxygen since you have two even numbers now. But you actually don't want to do that yet because you've unbalanced hydrogen. You have to rebalance the easy ones before you go after the hard one again. So what do I do to balance hydrogen again?
I need to put a 2 in front of it.
Yep, 2 in front of it. All right, and so that's going to change the carbon to what?
8.
And the hydrogen?
Oh, 20.
20. And then, so that means I've unbalanced my carbon now. So I have to rebalance that. So what do I have to do?
Multiply it by 2, so 8.
Yeah, so this 4 is going to have to be changed to an 8. I now have 8 carbons on the product side. But this 8 also multiplies the oxygen. So how many oxygens do I have now on the product side?
26.
26. 20 flipping 6. So now I'm going to go ahead and change my 18 to a 26. Now I can balance my oxygens. So how many oxygens do I need? What do I need to put in front of O2?
13.
13. And now I have my balanced equation.
Jeez.
It's kind of a bit much, huh?
Yeah, so you're telling me sometimes people don't do that on paper? They do that in their head?
Yes, but like I said, it
Oh,
it takes practice. Once you start to see the patterns, it starts to become a little bit easier, a little bit more automatic. Plus, there's also cases in which there are equations that are really simple to balance because you only have to like use one number. But honestly, for some of the more complex equations, even I will list out my elements. There's also another
that's
way
good to
to
hear.
solve. Yeah, there's also another way to solve the really, really difficult ones using algebra. But I don't know if you want me to show you that uh, because it requires you to have some significant, shall we say, mathematical chops to be able to handle it in terms of algebra.
Well,
Uh,
I think I'd be at least interested.
okay, all right. Well, in that case, I could pop up an
But I
equation.
also understand. I also understand if you got to take the time to do something else, that's perfectly fine.
Well, so let's go ahead and put it to a vote. Does anybody want to learn Does anybody want to learn the mathematical way of doing it, just in case you come across a really challenging problem?
I do.
If nobody, oh, yes, okay. So we got at least two yeses, and I'll go ahead and run with it then. Okay, so here's the deal. I'm going to give a similar type equation to the one that we just did. Okay, and here's how you approach it. Let's say I had something like this. Okay, C. I'll just keep it relatively simple for the purposes of not making it ridiculous yet. But let's say I have C2H6 plus O2. Actually, you know what? I'm just going to make it a little bit. Well, no, I'm just going to leave it like this. I don't want to go too off the rails. And then I have CO2 and H2O. what I do is I put a variable in front of each one of these coefficient places. So like for example, I'm going to go ahead and use um, I'm going to go ahead and use A, B, C, and D. I'll use lowercase letters so we don't confuse them. Okay, so this will be a little a. That'll be the coefficient for that. Little b will be the coefficient for oxygen. Little c will be the coefficient for CO2. And little d will be the coefficient for water. So what I'm going to do is I'm actually going to write out an equation, or several equalities, so to speak. So I'm going to write out an equation for oxygen, for example. So here's my equation for oxygen. The reactants always have to equal the products, right? Law of conservation of mass. Same number of atoms of each type on each side. So for every B, for every A, I have 0 oxygens, right? So I could say 0 times A, which of course is 0. I'll cancel that out. Plus, how many oxygens are in O2? 2. So it'll be 2 times B is equal. So how many oxygens are in the carbon dioxide? 2. So that means it's going to be 2 oxygens for every C. And then how many oxygens for water? Well, 1. So that means it's going to be 1 oxygen for every D. So 1 times D. And does it make sense why I did that? Can you see why that works as an equation? So the oxygens on the reactant side have to be equal to the oxygens on the product side. I need feedback, people. Does that make sense? James? Marva? Okay. You can type it in the chat if you want. Okay. Or you can speak. That's
I'm
fine.
confused about this. Can you return?
Yeah, sure, absolutely, no problem. All right, so essentially, I want to make sure that the number of oxygens on the reactant side are equal to the number of oxygens on the product side. Okay? So I looked for how many oxygens are present in each of these substances. I'm basically trying to solve for what these coefficients are. Okay? And so there's no oxygens in C2H6. So that's why I put a 0 times A. But there's 2 oxygens in O2, so that's why I put a 2 times B. Because this is an expression. This here is an expression for how many oxygens you have on the reactant side. This is an expression for how many oxygens you have on the product side. The product side is going to be 2 times whatever C is, because there's 2 oxygens that gets multiplied times C. Remember, these coefficients are multipliers, so it multiplies times this, and it multiplies times this. So for oxygen, my expression for the number of oxygens on the reactant side is 2B. On the product side, it's 2C plus D. So now I'm going to do the same. So now I'm going to do the same thing for hydrogen. So what would be the expression for the number of hydrogens on the reactant side? Exactly, systems of equations. What would be the expression for the number of hydrogens on the reactant side?
6A?
Yep, because there's 6 hydrogens in A, so it would be 6A. There's no hydrogens in the compound that B is in front of. That'd be 0B or just 0. What would be the expression for the number of hydrogens on the product side?
It's just going to end up being like 2D.
Yeah, 2D. because there's only hydrogen and water, and there's 2 hydrogens for every water, so D times 2 is going to give you the number of hydrogens, so 2D. And then I'll write one more expression for carbon. What's the expression for the number of carbons on the reactant side?
2A.
2A. A times 2. Yep. And then there's no carbons in O2, so I can ignore B. But what's the expression for the number of carbons on the product side?
C.
C. And that's it. So I have my system of equations. I have 3 equations. And 4 unknowns. But I can actually do this here because of these relationships. So what I can do is I can solve for each one of these in terms of, what I want to do is I want to solve for each one of these in terms of one of the variables. And it doesn't matter which one I pick, but it looks to me like it might make sense for me to go ahead and solve for each one of these in terms of A. Okay. So, what's that question? Yep, substitution. So I can go ahead and I can say, okay, well, I'm going to solve for each one of these in terms of A. So C is already equal to 2A. Makes sense. So C is equal to 2A. So now I'm going to solve for D in terms of A. So for this one, I would just take 6A is equal to 2D and solve for D. To solve for D, I just divide both sides by 2. And this is going to give me 3A is equal to D. So D is equal to 3A. And then what I'm going to go ahead and do is I'll solve for B by substituting C and D in to the first equation. Solve for what B is in terms of A. So 2B is equal to, and I'm using this equation here. I'm going to substitute in for 2C. Instead of C, I'll plug in 2A. And then instead of D, I'm going to plug in 3A. So then, once I've done that, I see, well, 2B is equal to 4A plus 3A. Well, that means that 2B is equal to 7A. And then I can divide both sides by 2. And then that gives me B is equal to 7/2 A. So now I have all variables solved in terms of A. And here's where you have to do something a little bit weird. Here's where you have to do something a little bit weird. You know that you want your balanced equation to be the lowest whole number ratio. So just plug in a 1, the number 1 for A. Plug in the number 1 for A. And then solve for everything, else based on that, okay? One for any of these other ones, and then solve for there, just make it more complicated since we've already solved for A. So that means if I plugged in a 1 for A, that means 7/2 times 1 is just going to be 7/2. Plug in 1 for A, it's 2 times 1 is going to be 2. Plug in a 1 for A, 3 times 1 is going to be 3. And then A, of course, is going to be equal to 1. Okay? And so then I can go ahead and plug that in. I can go ahead and put those numbers in for the equation. And I can say, well, okay, so it's C2H6 plus B, it says is 7 halves, so 7 halves O2 goes to form C is 2, so that'd be 2 CO2s plus D, of course, is going to be 3, so it's going to be 3 H2Os. Now here's the thing, you can't actually have a balanced chemical equation where there's a fractional coefficient. So if I wanted to make this a whole number, what would I have to do to each of the coefficients?
Multiply by 2.
Exactly. So I multiply by 2, and so this becomes 2, this becomes 7, this becomes 4, and this becomes 6. And I balanced my equation. Now, admittedly, it does not make sense to do this unless you're balancing an extremely difficult equation that you know is going to be a pain. Because as you can see, this takes a little bit of time. But this is definitely a valid way to balance an equation. Usually it's easier to just list your variables, but there are cases in which this is a much easier method because it offers mathematical precision. Cool. So let's do a little bit of predicting products because I do think that that's important. It's also actually going to be especially important for upcoming chapters, so we definitely want to look at that. So let's take a look at predicting products. So there are 5 basic types of chemical reactions. Well, technically speaking, there's more than that. But I'm going to teach you 5 basic types of chemical reactions. And so the first one is substitution, or first one is synthesis. And synthesis is sometimes also called a combination reaction. And the general formula for this is basically, the general formula for this is A plus B goes to form C, or goes to form AB rather. So 2 elements or compounds come together to form a single product. You can always tell a synthesis reaction because there's always only one product. Only one product. Okay. Now, if you're trying to predict the products and you only have the reactants to go by, while this the only way you can really be certain it would be a synthesis versus some other type of reaction without a much broader knowledge base is if these first 2 things were elements. So for your purposes, if you're trying to predict the products, you're given an equation, the A and B are often 2 elements. So you'll start with 2 elements and you'll end up with, you'll end up with one product. An example of this is kind of the one that we already balanced, the 4 aluminums and 3 oxygens go to form aluminum oxide, Al2O3, 2 of them. So the coefficients aren't always 1, they can be lots of different things, but that's an example of a synthesis reaction. Okay, let's take a look at the next type. So that's type number 1. Okay, there we go. So now type number 2. There we go. So this would be decomposition. And decomposition reactions, this is actually what, Ethan, what you were talking about earlier. Decomposition reactions are the opposite of a synthesis reaction. And so this is actually AB goes to form A plus B. So a compound breaks apart into multiple pieces. And this is actually one of the easiest ones to recognize as a synthesis, or as a recognize what type of reaction it is, because a decomposition reaction, there's always only one reactant. Whenever you're asked to predict the product of something where there's only one reactant, you know this is going to be decomposition. Now, when it breaks apart, it could break apart into elements or compounds, and break into elements or compounds. But for your purposes, you can assume elements. You can assume it breaks up into its component elements unless told otherwise. So, yep. All right. And easy example of that would be like the decomposition of silver chloride, which silver chloride, if you're not familiar with, is a substance often used in, or it used to be used in photography before everything went digital. And silver chloride actually is unstable in the presence of light. So what happens is it'll break apart. Silver chloride will break apart into silver metal and chlorine gas. So that's another type of reaction. All right, next we have whoops. Next we have single replacement. And so for a single replacement reaction, the reactant is the pattern is usually like A plus BC goes to form AC plus B. Although sometimes you can actually see something a little bit different. You can actually see A plus BC goes to form BA and C. It just depends. It depends because the principle of this reaction is that like replaces like. So what does that mean? It means that if something is a positively charged ion or can become a positively charged ion, it will replace another positively charged ion. Or metal replaces metal, non-metal replaces non-metal, if that's easier for you. You just have to remember sometimes hydrogen acts like a metal. And it's not polar and non-polar, because I know what you're thinking. Like dissolves like. So polar things dissolve, polar solvents dissolve polar solutes, and non-polar solvents dissolve non-polar solutes. But in this case, even though it's a similar phrase, it actually refers to something different. Like replaces like here means that, for example, if typically the elements in front are metals. So let's say, for example, let's say B is a metal. So in this case, this would be if A and B are both metals. A is going to switch places with B, so B gets displaced and kicked out. So B and A are still both metals, but they switch places. And this would be like if A and B are metals. A and B are metals. And so that's what this kind of is representing. If, however, A and C are nonmetals, then A is going to switch places with C. So So the second situation is what would happen if A and C were nonmetals. Does that make sense? Now, one important thing to note here is, well, that's actually two kind of important things. If you're trying to determine, is this a single replacement reaction, it's actually pretty easy to tell because a single replacement reaction always involves the reaction of an element and a compound. An element and a compound are what are reacting. Okay. But one thing you actually have to watch for is, since this like replaces like thing just tells you what's replacing, these are not necessarily, when they switch places, you have to cause them to switch places according to their charge. So they have to switch places according to their charge. So like, for example, if I have aluminum here and I'm reacting with magnesium chloride or something, okay, I'm reacting with magnesium chloride, and this, yeah, I think this reaction actually would work. What's going to happen here is that aluminum and magnesium are going to switch places, but you have to take into account the charges of these guys. So aluminum, well, right now it has no charge, but when it does have a charge, it's usually a +3, right? And magnesium here in this compound is a +2 as is. It's a +2 because it's part of an ionic compound, and chlorine's a -1. So if magnesium and aluminum are going to switch places, aluminum is going to go with chlorine, and if aluminum goes with chlorine, then that means that it's going to have to come together with chlorine based on the charge. Now, aluminum's a +3 charge, chlorine's a -1, so that means I need 3 chlorines for every 1 aluminum. I have to look at these as separate ions, so I need 3 Cl- ions for every 1 aluminum ion. Because I need 3 times -1 to give me a -3 to balance the +3 of aluminum. And then, of course, magnesium is going to get kicked out on its own. So when you're predicting the products of these types of balanced equations, you have to make sure that when you're putting them back together, these single replacement reactions, when you're putting them back together, you have to do so according to the charges. Does that make sense?
It makes sense to me. I'm all good.
Okay. Now, of course, this is going to require you to do some crazy fancy balancing, because now I see, well, I have an odd number of chlorines here and an even number here. So essentially, that means that I'm going to double the odd. So 2 chlorines, that gives me 6, which means I need 3 of these guys. And then that means I'm going to have 3 magnesiums here and 2 aluminums here. Now, you might end up needing to list out your elements to balance that, or might be able to balance it in your head. It just depends. And just use whatever you need to, and that's totally fine. It takes a while to really get comfortable enough to start balancing these in your head. All right. So, number 4 type of reaction. This is very similar to the single replacement reaction. It's called a double replacement. And by the way, sometimes you'll see it listed as a displacement, double displacement, or double replacement. It doesn't matter which term is used, it means the same thing. But the same principle applies here, in that you're going to have to use the like replaces like rule. The like replaces like once again. Okay, so the general format for this is going to be AB plus CD goes to form AD and CD. And typically this always involves 2 ionic compounds or ionic compounds and acids. So basically anything with ions. Ionic compounds or acids are the ones that have the ions. So this is where you're going to get your double replacement reaction. Generally speaking, that means 2 ionic compounds. but it can mean an ionic compound and an acid. Oh, there we go. All right. So it's two ionic compounds usually, like replaces like, same type of thing. It's actually an example of this type of reaction is the same one that we did over here at the beginning of our session. When we balanced this one, sodium hydroxide, hydrogen sulfate produced sodium sulfate and water. So that is a double replacement reaction. Like replaces like. The sodium is a positive charge, hydrogen is a positive charge. They switch places. Keep in mind, hydrogen often acts like a metal. So in like replaces like, you're almost always going to use hydrogen as a metal. It will replace other metals. Why doesn't it happen with covalent? It's not that it can't happen. It's more that double replacement reactions or double displacement reactions actually also have another name that you're going to actually be expected to know. These are also called metathesis reactions. And what that means is that they're ion switching. Okay, it's not that you can't have a similar type of reaction happen with covalent compounds, but covalent compounds don't usually do this clean switch, metathesis, or switching reaction. Because covalent compounds don't break apart into ions, when they do break apart, they tend to break apart in untraditional ways, or when I say untraditional, or rather unexpected, unpredictable ways. And therefore, covalent compounds, it's really hard to sometimes predict exactly what they're going to do because they can, just like they can come together in multiple ways, NO, N2O, NO2, N2O5 are all real compounds. Just like they can come together in multiple ways, they can break apart in multiple ways, and it kind of depends on the situation. So that's why we usually don't worry about covalent compounds, because even if it does engage in some sort of a reaction that kind of looks like this, kind of looks like it could be a double replacement, it's not so much a double replacement usually because, or at least it's not a predictable one, because when they come together, when they break apart and come back together, they do so in unpredictable ways that sometimes changing the reaction conditions a little will result in a different product. Okay, so last but not least, we have combustion. And combustion is probably the easiest one to figure out. Combustion is the easiest one to figure out. And the reason, yeah, that's right. Hydrogen acts like a metal because it usually lets go of its electrons. It's much more likely to let go than to grab electrons. It's very hard for hydrogen to grab electrons. It can do it sometimes, but it doesn't usually like to. And actually, at extremely low temperatures, hydrogen actually is a metal, or it acts like, it actually behaves like a metal. It's metallic at really, really low temperatures, especially really low temperatures and high pressures. But a combustion reaction has a very simple pattern. It's CXHY, some sort of hydrocarbon plus oxygen goes to form carbon dioxide and water. Now, occasionally, you may have oxygen also in this. It might have an OZ, but usually it's just a CXHY. So a hydrocarbon, anything with carbon and hydrogen reacting with oxygen, you should assume that this is likely a combustion reaction. This is a combustion reaction. And it looks like we're not going to get a chance to do much in terms of oxidation and reduction, but these are the basic types of reactions. And this is how you can identify which one you have. Two ionic compounds would be a double replacement. Element in a compound, single replacement. Only one reactant, decomposition. Only two elements, that'd be synthesis. And hydrocarbon and oxygen, that's combustion. Let's do one quick thing if we can find the time to do it. Let's look at some of these and just look and see what type of reactions these would be. Okay? So if I have hydrogen and oxygen, what type of reaction would you predict this would be? Yeah, exactly. That would be a synthesis reaction. And if I had a loose sulfide, which coming up with the equation, you just have to figure out the charges. Al2S3, because aluminum is a 3 plus and sulfur is a 2 minus. What type of reaction would this be? What would number 2 be? Yeah, decomposition. It only has one reactant, so it's going to break apart. And you could assume that it would break apart into elements. 2 aluminums, 3 sulfurs. Now, here's an interesting one. It says iron 3, which means not that it has a charge right now, but when it reacts, it will have a charge. And it reacts with water, H2O. This is a little bit confusing because it's not necessarily something you'd expect. Now, what type of reaction would this be? I have an element iron and I have a compound water. What would this give you? What type of reaction? Yeah, this is a single replacement. And since iron would actually be like hydrogen, and that hydrogen would tend to be positively charged or behave like a metal, it switches out. And if iron's a 3 plus, oxygen's a 2 minus, it'd be Fe2O3, which is rust. And this is the reaction that causes iron to rust in the presence of water. And then, of course, the other thing produced here would be hydrogen gas. Okay, cool. Yep, very good. Now, what about number 4? What would that be? Sodium sulfate and calcium chloride. Sodium sulfate, H2SO4. Yep, that's double replacement. We're in the lightning round, people. Double replacement. Of course, this was single replacement. And then calcium chloride, because that's another ionic compound. If you were to make a guess, what would you expect number 5 to be? Yeah, also double replacement. It's 2 ionic compounds, or in this case, actually an acid and an ionic compound. What about number 6? C6H4 and oxygen. Exactly, combustion. Hydrocarbon and oxygen, this is going to be a combustion reaction. And then you just have to remember that when for a case like this, the sodium sulfate calcium chloride, sodium is a +1, sulfate's a -2, calcium is a +2, chlorine's a -1. When I put these back together, I have to put them back together according to their charges. So sodium is going to go with what element? Here. Sodium is going to go with one element here.
Sodium? I'm confused.
Well, no, when this is a double replacement, so the ions are going to switch places. Right?
Gotcha. Sorry, it's going to switch with calcium.
It's going to switch with calcium, which means sodium is going to combine with what element on the product side?
Chloride. Or chlorine.
Chlorine, exactly. Well, chloride is fine too, but yeah. So sodium, if sodium's a +1 and chlorine's a -1, what would the formula of the compound be?
Should it not just be, it would be calcium sulfate. Oh, I'm sorry. Wait. So yeah, wouldn't it be perfectly balanced?
It is.
Oh, okay.
What I sometimes see as a mistake is students will see the 2 on the other side on the right, Na2Cl2, but that's not correct. You can't actually do that. That's not right. So it's just NaCl. And then, as you said, calcium is a +2 and sulfate's a -2. So they're already balanced as well. So it's just CaSO4. So when you're putting them together, don't pay attention to how many are on the reactant side. pay attention to what is the charge, and then put them together according to their charges. Cool?
Sounds good to me.
Do a quick balance, so just be a 2 in the front of the NaCl and you're good. All right, awesome. Well, thank you so much for coming. Appreciate it. And I apologize, we had to kind of rush it a little bit at the end there. But one thing that will really help you with this type of stuff is just to do some practice. There's a bunch of practice up on our website. I can actually show you right now. I'll do a quick breakdown, share my screen with you so you can see what I'm talking about. All right, under Chemistry Web Resources, if you go down to Chem 1411, you can look at practice problems. Under Chemical Equations, Stoichiometry, and Combustion Analysis, there's lots of practice here. So there's some in the overall comprehensive review, but there's balancing chemical equations, writing and balancing chemical equations, predicting products by reaction type, and predicting products mix, which is the one that we did, and also predicting products using an activity series. So there's a lot of different practice problems, and there's answer keys for each one of them. So if you want to check that out, you want to practice any of these and get really good at it, feel free to definitely go ahead and do so. All the equations are balanced. You can check out the answers, make sure you're doing it correctly, and that should put you in a pretty good position to kind of take it out from here.
Thank you so much, sir. I hope you have a great week.
Yeah, you too, and we'll look forward to seeing you all next week. Hopefully we'll see you again next week. Thank you.
Thank you.
Have a good night.